Hello, this is a molecule of chloromethane. The lime green atom is the chlorine, the gray atom is carbon, and the three white atoms are the hydrogens. It is approached by a cyanide anion. In cyanide, we have nitrogen, which is blue, and carbon, which is gray, and the negative end of the ion is on carbon. Because chlorine is more electronegative than carbon, the chlorine-carbon bond is polarized with a partial negative charge on chlorine and a partial positive charge on the carbon. Therefore, the carbon is electron deficient. In cyanide, cyanide has a -1 charge, and it has a lone pair, which is shown in the diagram, on carbon, which is the negative end of the cyanide ion. Here we are at the transition state. We see that to the left there is a partial carbon-carbon bond forming, while at the same time on the right the carbon-chlorine bond is breaking. Notice that the carbon in the center is approximately sp2 hybridized. Cyanide is the conjugate base of the weak acid hydrocyanic acid. Therefore, it is a strong base and is a good nucleophile. On the other hand, chloride is the conjugate base of the strong acid hydrochloric acid, and therefore chloride is a weak base and a good leaving group. We show the flow of electrons with curved arrows. We see a curved arrow from the nucleophile to the electron-deficient carbon. That will ultimately form a new carbon-carbon bond. To the right, we see a curved arrow going from the bond onto the chloride ion. Therefore, that is a bond being broken, and chlorine will depart as chloride with a complete octet. This figure shows both the arrows and the dots for the lone pair on the nucleophile. Here is a potential energy diagram for an SN₂ reaction. Along the x-axis, we have the reaction coordinate, which goes from left to right as the reaction proceeds. Along the y-axis, we have the relative enthalpies in units of kcals per mole, and the reactants are set to be the reference of 0. On the path from reactants to products, there will be a molecular configuration of highest energy, which we call the transition state. The relative height in energy of the transition state above the reactants determines how quickly the reaction proceeds. Because the transition state is energetically unstable, the molecular configuration at the transition state has only a fleeting existence, which makes it difficult or impossible to experimentally isolate. However, we can determine the configuration using quantum mechanical calculations. The distance or height in energy required to go from reactants to the transition state is the energy of activation, which is shown in green in the diagram. The greater the energy of activation, the higher the hill and the slower the reaction. The lower the energy of activation, the lower the height of the hill, and the more rapid the reaction. We have calculated the molecular properties of a series of halomethanes. For fluoromethane, the fluorine atom is shown in light blue, and the carbon-fluorine bond has a length of 1.395 angstroms. Here is chloromethane with the chlorine atom shown in green, carbon in gray, and hydrogen in white, and we notice that the carbon-chlorine bond has a length of 1.806 angstroms. In bromomethane, the carbon-bromine bond length is 1.965 angstroms. Notice that the bond lengths are getting longer between carbon and a halogen as the halogens go down the periodic table from fluorine to chlorine to bromine, and we'll see in our next slide it continues with iodine as well. Here is iodomethane, which has the largest carbon-halogen bond of any of the halomethanes. Not only do the bond lengths get longer as we go from fluorine all the way down to iodine, but the bond strengths decrease. So the carbon-fluorine bond is the strongest, the most difficult to break, while as the carbon-iodine is the easiest to break. This also parallels that fluorine is a relatively strong base, whereas the basicity of chlorine, bromine, and iodine decreases. Here we have the actual potential energy surface for the SN₂ attack of chloride on iodomethane. The energy of activation is seen to be approximately 22 kcals per mole, and we also notice that this is an exothermic reaction. Our reactants are iodomethane and chloride. We see the chloride ion coming in, the lime green from the left, and we see it in the proper configuration for an SN₂ attack on iodomethane. Once the atoms pass through the transition state, they proceed to form the products of chloromethane and iodide ion. Notice that the configuration of the hydrogen atoms around the carbon atom are changed from the left-hand side to the right-hand side. So we see the stereochemical inversion at the electron-deficient carbon that is undergoing the SN₂ reaction. We know that complete stereochemical inversion is definitive for SN₂ reaction. Cyanide is a good nucleophile, and chloride ion is a good leaving group. Therefore, we study the SN₂ reaction of cyanide attack on chloromethane. We notice that the energy of activation is approximately 35 kcal per moles, and that this also is an exothermic reaction. Our reactants are cyanide on the left and chloromethane on the right. The reaction proceeds through the transition state shown, where we have a partial carbon-carbon bond formed between the incoming cyanide, and we have a breaking carbon-chlorine bond between carbon and the leaving group, chloride, and it proceeds to the product of acetonitrile plus chloride ion. The remainder of the slides in this video will show the computed transition states for a number of SN₂ reactions. Enjoy. Thank you very much for your attention. Have a good one.